driven damped oscillator. We write our equation of motion for dynamic variable x, and on the right hand side we have the force f of t. This is non-homogeneous ordinary differential equation. We can rewrite it in terms of differential operator d, linear and of the second order, acting on x, which gives us f. From the theory of differential equations, we know that the solution to this equation is given by two parts: particular solution and homogeneous solution. Particular solution means particular for the given form of f of t. And homogeneous means when f of t is 0. This is known as general solution. We can see that if we act with the differential operator on the sum of solutions, particular and homogeneous, we will get, due to linearity, that d acts only on the particular solution, plus it only acts on homogeneous solution, which gives us function f for particular solution and 0 for homogeneous solution, which is the solution we want. Note that particular solution xp is specific to the driving force f of t. If we choose new function f of t, it means that we have to find new particular solution. And this situation is less than ideal because possibly we have to deal with non-analytic solutions. So our approach will be to decompose arbitrary function f of t into sines and cosines, which is known as Fourier transform, then use superposition to synthesize whatever particular solution we need. This approach is general approach to solving non-homogeneous equations using Fourier transform. We can illustrate it as following. Dynamic variables we can write in time domain, where we have independent variable time, where we have specific force, driving force as a function of time, and equation of motion is ordinary differential equation, which is hard to solve for arbitrary f of t. The alternative is to work in frequency domain. There we write variable as a function of one frequency, omega. To go from time domain to frequency domain and back is performed via Fourier transform. The force we decompose into harmonics of omega. The equation of motion will become algebraic. Because we know how to differentiate sines and cosines of omega, which is easy to solve. This general approach works not only for damped driven oscillator, but for any inhomogeneous ordinary differential equation system. Let's write our equation of motion in complex form. We can write complex variable z as given by a sum of real part x of t and imaginary part y of t. Of course, we understand our solution to be just the real part of z. Thus, we can write the equation of motion as z double dot plus 2 beta z dot plus omega naught squared z. And on the right hand side, we'll write the driving force at the specific frequency given by a times e I omega t. Now note that we understand the driving force to be only a function of one frequency. Omega is the driving frequency. But if we solve this problem for one driving frequency, turns out we solved the entire problem because of superposition. If we decompose the driving force into sum of sines and cosines via Fourier transform, we search for solution to this problem in the form of exponent c times I omega t. Substituting the form into the equation, we get c times minus omega squared plus 2 beta I omega plus omega naught squared. And that should all be given by A. This is how the equation of motion looks in the frequency domain. And we see that it's no longer a differential equation, but rather it's an algebraic equation. Solving for C, we find that it's given by amplitude A divided by omega naught squared minus omega squared plus 2 I beta omega. Let's write coefficient C in polar form. It's going to be given by amplitude A times E raised to power of minus I delta, where the minus in front of I is just a matter of convention. We can see right away that A squared is simply going to be given by C complex conjugate times C. So we can write amplitude A in terms of driving force coefficient small a, and then in the denominator we have omega naught squared minus omega squared plus 4 beta squared omega squared, and we take square root of all of that. We see that A is a function of omega. It has a peak at resonant frequency. In terms of dependence of amplitude A on driving frequency omega, at omega resonance, we have maximum of this curve. And then as we decrease beta parameter, the peak becomes sharper. Note that we also expect the resonant frequency to be shifting to higher frequencies for decreasing beta. Another thing to note that the resonant frequency is not the same as the frequency of free damped oscillations. Recall that we had frequency of free damped oscillations be given as omega squared minus simply beta squared. So that's a difference. The solution itself we'll write as the real part of Z, which is given by A times cosine omega t minus delta. Delta itself is easily found to be arctangent of 2 beta omega divided by omega naught squared minus omega squared. Phase of the oscillation as a function of frequency omega is given as following. At very low frequencies, the motion is in phase. On the other hand, at very high frequencies, the motion is exactly out of phase. At frequency omega naught, which is the frequency of undamped oscillations, the frequency delta is exactly 90 degrees. Now, as one keeps decreasing beta, this curve becomes sharper. Another important concept is quality factor. Quality factor is defined as a dimensionless quantity as resonance frequency omega sub r divided by 2 beta. Turns out that 2 beta is exactly the width of the resonance curve. So this formula can be rewritten as resonance frequency divided by delta omega, where delta omega is full width of maximum of the resonance curve. Another definition of the quality factor is given in terms of the ratio of energy stored over the power loss, equal to resonant frequency times the ratio of energy stored in the oscillations divided by power loss, which has the physical meaning of number of oscillations before energy is dissipated. For example, tuning fork has Q of about 1000. Superconducting RF cavity has a Q of about 10 to the 10. Thus, we will always write our general solution as consisting of two parts, homogeneous part and particular part. Note that for beta parameter not equal to 0, the first term decays. On the other hand, the particular solution we found to be proportional to I omega t, where omega is the driving force frequency, which means that this solution doesn't die out, so it's a long-term solution.